Alright guys, if you are watching this video, this is because you missed class on Monday or Tuesday where we learned how to draw electron dot structures in class. So here's the tutorial that you missed. So the very last page of your notes looks like this. It's blank. This is where you need to be writing down the instructions and examples for how to draw electron dot structures. So the first thing we want to look at is a couple of definitions and rules. So the first definition we're going to look at is called the octet rule. And basically it says atoms will bond with another atom to get a full set of 8 valence electrons. And we're going to look at different types of bonding. In this particular unit, we're talking about covalent bonding. And so, as you learned in the notes, covalent bonding is all about sharing electrons. And so in our unit here, the atoms are going to share their electrons with another atom to try to fill up their valence shell. Okay, that's the octet rule. Now, when we're drawing these dot structures, we're basically drawing how the atoms are sharing with each other. And we have some rules that we're going to follow. And I'm going to show you examples of these rules. So you need to write these down. The first thing we're going to do is we're going to add up the total number of valence electrons for the entire molecule. And then we're going to determine which one is the central atom. Now there are a couple of things we have to pay attention to. One, the central atom will never be hydrogen. And usually there's only one of them, and it's often written first. Now once we've done those two things, we're going to start drawing. So we're going to attach the outer atoms to the central atom with single bonds, and I'll show you what that looks like. Then we're going to give all of the outer atoms an octet using lone pairs, and lone pairs are electrons that are already paired up that are not involved in bonding. If we have any leftover valence electrons, we're going to put them on the central atom as lone pairs, and if we don't have enough valence electrons, then we're going to make double or triple bonds by sharing more with the outer atoms. And you're going to see examples of all of these different rules. So make sure you have them written down, and I will show you what they mean in our first example. Alright, so here's our first example, NH3. So the first thing that we need to do, our first step that we just wrote down, is to add up the total number of valence electrons. So if we look at our periodic table, here we go, we want to find the number of valence electrons for nitrogen. Okay, so here's nitrogen, and we can count 1, 2, 3, 4, 5. So the nitrogen has 5, and then the 3 hydrogens each have 1. So for our total number of valence electrons, we're going to have 5 plus 3 times 1 for the hydrogens will equal a total of 8 valence electrons. Okay, so the next thing we're going to do is determine which one's in the middle. We said it can't be H, so in this case it's N, and then we're going to attach those hydrogens with single bonds. Now a single bond is a bond that has 2 electrons being shared. Okay, so we're going to draw our N, and then we represent a single bond with 1 dash. So we're going to bond our 3 hydrogens to the nitrogen with single bonds, and that dash represents 2 shared electrons. Okay. And then we want to look at the outer atoms. Now, hydrogen is kind of special. Because it's only in the first shell and it only has an s orbital, hydrogen can only have 2 electrons. It can't have more than 2. So we will never add more dots to H. The only thing that hydrogen can get is a single bond. Okay? So all the hydrogens have the 2 electrons that they want, and we've only used 2, 4, 6 of our 8 electrons. So we put our 2 leftover electrons on the nitrogen as a lone pair. So a lone pair you're going to draw as 2 dots, and they're not involved in bonding. They're just on the nitrogen. They're already paired up. Okay? So we've basically gone through steps 1 through 5 in our rules. We don't have to do step 6 because we had enough electrons. The nitrogen has 2, 4, 6, 8. It's following the octet rule. The hydrogens all have 2. They're following the octet rule. And that would be an electron dot structure for NH3. Alright, so for our next example, this was example 1, example 2, we're going to look at CH4. So the first thing we're going to do is add up our valence electrons. So look at your periodic table, Count how many valence electrons carbon has. It has 4, and then each hydrogen has 1. So we have a total of 8 valence electrons to work with. Carbon is in the middle. We single bond our 4 hydrogens, 1, 2, 3, 4. And we count. All the hydrogens have the 2 that they need. The carbon has 2, 4, 6, 8. So we've used our 8. The carbon has its octet. The hydrogens have their octet. So that would be our completed dot structure. All right, so now our third example is going to be CO2, carbon dioxide. So we add up our valence electrons. Carbon has 4. Each oxygen has 6, so that's a total of 16 electrons, okay? So this time, we want to figure out which one's in the middle. There's only one C, so it has to be in the middle, and then the 2 oxygens are bonded to the C. So we're going to put the C in the middle, and then we're going to single bond the 2 oxygens, okay? Now, we're not dealing with hydrogen, so this time we do need to add lone pairs to our outer atoms. So we're going to add 1, 2, 3 lone pairs to that oxygen. 1, 2, 3 lone pairs to that oxygen. So now each oxygen has 8. Okay? So let's count how many electrons we've used. 2, 4, 6, 8, 10, 12, 14, 16. We have used up all of our electrons. Each oxygen has 8, but the carbon only has 4. So how can we give the carbon more electrons if we don't have any more to give it a lone pair? So what we're going to do here, we're going to put a little star, and we're going to use double bonds. So a double bond is 4 shared electrons rather than just 2 like a single bond. So what's going to happen is the oxygen is going to take some of its electrons and it's going to share them with carbon. And so what we end up with is now carbon is going to have 2 double bonds. So the carbon has 4, 8, right? So 2, 4, 6, 8, those are double bonds. The oxygens still have 8. They didn't lose them. They're just sharing them with the carbon. So now all 3 of our atoms have 8 electrons and our dot structure is complete. So you can see the difference. Up here we use single bonds. That's 2 electrons with 1 dash. Here we did double bonds. That's 4 electrons with 2 dashes. Okay, now our next example, we're going to look at a polyatomic ion. And in your notes, you wrote down all of the polyatomic ions. So this time we're going to use the nitrite ion. Okay, it's NO2, it has a -1 charge. Now when we're adding up our valence electrons, nitrogen has 5, each oxygen has 6, and then the charge represents more or less electrons than the neutral atom. So if the charge is negative, there are more electrons. If the charge is positive, there are less. So because of that charge, we need to add another electron to get a grand total of 18. Okay, so now we're going to put nitrogen in the middle. We're going to single bond our oxygens, lone pairs on the oxygens. Okay, so let's count. 2, 4, 6, 8, 10, 12, 14, 16. We still have 2 more that we can use, so we can put a lone pair on the nitrogen. Okay, now we're out of electrons, but the nitrogen only has 6. So what can we do to give the nitrogen 2 more? We can't add any more dots, but just like before, one of the oxygens can share, and we can make a double bond with one of the oxygens. The other oxygen stays single bonded. Oh, not that one. All right, so this is now our completed dot structure. So the nitrogen has a lone pair, it has a single bond and a double bond. So that's 2, 4, 6, 8 electrons. And to show that this whole thing is an ion with a negative charge, we're going to put it in brackets and show its charge. So those brackets are only for polyatomic ions. Okay, so now we need to define a new term, and this new term is resonance structure. So NO2, -1, represents a resonance structure, and basically what that means is there's more than one correct way to draw the dot structure. So if we take a look at our structure, we could have put the double bond on the other oxygen and it would have been exactly the same, and both structures would be correct. So our example here for our resonance structure, it could look like we drew it or we could have put the double bond on the left oxygen. Either of those are correct. So we would say that NO2 -1 is a resonance structure. It has more than one correct way of drawing the dot structure. And what happens in reality is this lone pair here and here, or not a lone pair, this pair of electrons here and here, it really kind of spreads itself out to both bonds. So we end up with these two structures that are identical because we get a double bond and a single bond. They could go on either oxygen. So that would be the definition of a resonance structure. All right, let's do another example. This time we're going to look at the molecule N2. So it's two nitrogens bonded together. So our electrons are going to be 2 times 5, so we have 10 total electrons. Okay. So this time, because we only have two things bonded together, there's really not one that's in the middle. They're just two bonded with each other. So we're going to start with two nitrogens bonded with a single bond, and then we're going to pick a nitrogen and add lone pairs. So 1, 2, 3 lone pairs. So we've used 2, 4, 6, 8. We can give a lone pair to the other nitrogen to make 10. Now if we look at our structure, this nitrogen has 8, but this nitrogen only has 4. It needs 4 more. So just like before, we're going to do some sharing. So the nitrogens are going to share 6 electrons instead of only sharing 2. And what that gives us, you can probably guess, is called a triple bond. So a triple bond is 2, 4, 6 shared electrons between two atoms. The triple bond is going to be the strongest of the bonds. It's sharing the most electrons. So these two nitrogens share 6 electrons. They have a triple bond between them. And as you can see, they're sharing 6. They each have a lone pair, so each of them has 8, and we've used all 10 of our electrons. All right, now our example that we use for nitrogen represents nitrogen gas that you find in the atmosphere, and it's what's called a diatomic molecule. There are 7 elements that in their natural state, just how they're found in nature, they're found as 2 atoms bonded together, diatomic. They're found as molecules. And so whenever we talk about hydrogen gas or oxygen gas or fluorine gas or bromine, iodine, nitrogen, or chlorine, in their natural state, they're not found as single atoms by themselves. They're found as diatomic molecules. And you need to memorize these because if we were to ever talk about oxygen gas, you need to know that that's O2 and not just O. Whereas something like neon would just be Ne. It's not diatomic. So these are the only elements that are found in diatomic molecules. The rest of the elements on the periodic table are found as atoms in their natural state. And one way you can remember this is if you read this as a word, it spells Hofbrinkel, just an easy way to remember what those diatomic molecules are. All right, so there's one more short little addition to this video. We're going to talk about some exceptions, so make sure you have these diatomic molecules and watch the last video to get the exceptions to the octet rule.